Hey everybody, it's Mrs. Harbin, and we're going to learn about a lot about solutions today. Okay, so look at these bullet points and see if you know any of them already, and we'll just emphasize what you need to remember. Okay, so um, here we go. Chapter 16 is your source of information for this unit. Please make sure to read it. Okay, so one thing we know already is that water is rarely pure, but often a solution. We talked about all of these in class, but here's the definition of solution. Make sure you know all the different kinds of solutions. Now, let's talk about what makes up a solution. The solute is the smaller part, and I always say you get dissolved. You solute you. And the solvent is the biggest part of a solution. If we say the word miscible, we're talking about liquid and the liquid mixing. Okay, liquid and liquid. So if two things are miscible, they're liquids that can mix. So I always say miscible is mixable liquids. Okay, so vinegar and water is a solution of miscible liquids. Okay, so please remember that all types of solutions are homogeneous mixtures, and you could have solids, liquids, or solids and solids, solids and liquids, liquids and liquids, gases and liquids, and gases and gases. So make sure you can think of an example of each kind of solution when you get the chance, okay? I think you probably know some more of these. Brass is a solution of solids. Different carats of gold are a solution of solids. Steel. Okay. So a lot of times when we're talking about solutions, we have to ask a bunch of questions. There's four main ones I'm going to be focusing on. One is, will it dissolve to make a solution? You tested this Friday in the lab, and we saw that salt dissolved in water and acetone dissolved in water, but hexane did not. So polar things will dissolve polar things, and here's water. Water's polar. You got a partial negative and a partial positive down here. So water's polar, so it'll dissolve other polar things. So what will this dissolve? And we'll look. This is also going to be polar. And so this and this will mix. Okay, they will dissolve. Those arrows go in four directions, equal but opposite. They cancel out, so this is nonpolar. So this will not dissolve in water. This is also, oh, we wouldn't draw any arrows on this one because this is a nonpolar bond, so this is also nonpolar. Okay, so these and these will dissolve. These will not dissolve because polar dissolves in polar, nonpolar dissolves in nonpolar, and polar does not dissolve in nonpolar. Okay, so the white bear dissolves in water because it's polar. What about the Wicked Witch? She totally dissolved in water. She must be polar. Okay, so dissolving involves attractions between charges, or so that there are no charges. If there are no charges, there's not much attraction. So that's why polar and nonpolar don't mix. Okay. So if polar and nonpolar don't mix, we get that they don't have the same charges. But why do nonpolar things mix in nonpolar things? Well, there's nothing to repel them. There's no opposite charges to repel. So they mix and kind of slide past each other, and a little bit of attractions are due to their London dispersion forces. So dry cleaning solvent dissolves nonpolar oil. Okay, so what if the dry cleaning dissolves the oil, then the dry cleaning solvent must be, you guessed it, nonpolar. Okay, if butanol dissolves in water, then butanol is, well, water's polar, so butanol's polar. All right, so how does it dissolve? How does it dissolve is the next question. In order for things to dissolve, well, you already got your solute, and it's attracted to each other by a bond. You already have your solvent, it's attracted by a bond. And so first, those forces of attraction have to be overcome. But once that happens, then new forces form between the solute and solvent, and that releases some energy, and so the solution is going to be happy. Okay, so one, overcome the forces holding the solute together as a solute, and the solvent together as a solvent, but then make new bonds as the solute and the solvent form a solution. How does that happen in molecular compounds? So we know that sugar dissolves in water. Yay, Kool-Aid. And so when the sugar dissolves, then water molecules surround it. So each of these sugar molecules is surrounded on all sides by water molecules, and that's because sugar's polar and water's polar. Sugar's polar, water's polar. Sugar's polar, water's polar. So it mixes. But the sugar doesn't break into smaller pieces. Each tiny molecule gets surrounded, AQ for aqueous. Okay. So when you're talking about dissolving molecular compounds, the polar things dissolve, then what happens is the attraction of all this liquid for itself is overcome by the attraction of the polar stuff for water. Okay, so this is called methanol. It's a covalent compound, has C's, H's, and O's. All right, it's covalent, but it is polar, so it gets surrounded by water. NH3 is a polar compound, and so it gets surrounded by water. But notice the only difference: pure, dissolved, pure, dissolved, surrounded by water. Okay, nothing else happens to the stuff. Each tiny piece gets surrounded. That's different than ionic compounds, because ionic compounds, when they go into water, they turn into their individual ions. So they dissolve and they break apart, break into ions. So two big words. Dissolve means it mixes. Polar dissolves polar, like nonpolar dissolves nonpolar. Sometimes we say like dissolves like. Ionic compounds dissolve in polar things because ionic compounds have charged ions and polar things are charged. But then ionic compounds dissociate or break into ions. So here's some NaCl ions, here's some water. When it dissolves, it actually, each ion gets surrounded by water, and so that the sodium chloride ions are not connected anymore. Okay, now that's for why ionic compounds that are soluble do dissolve. But wait, we talked about these things called solubility rules, and some ionic compounds don't dissolve. And so when would this not happen? Well, if the attraction between these ions, these ions right here, these ions, these ions, these ions, these ions, it's so strong that even water can't break it. Think about when you take a date to KOH, right, girls? You take a date to KOH, you have a pretty strong attraction, okay, for your date. Now, you're dancing around, people bumping into you, people asking you for a dance, all right? If no other solvent in the crowd can make you and your partner break up, then you're insoluble. Like these guys are definitely insoluble. But if there's more attraction for a solvent particle for that person and that person, then goodbye date, hello new water attraction. Okay, so here's your solubility rules. The ones that are soluble are the ones that the ions are more attracted to water than to each other. The ones that are insoluble, the ions are more attracted to each other than to water. Okay, so when water attacks, things dissolve if they're like water. You can see this thing is dissolving, but notice it's an ionic compound. It breaks into its ions, so now those are free to move. This is a molecular compound. Here's a molecule that's surrounded by water, so this must be polar with a dipole. This must also have a dipole, and so the opposite ends of the dipole are attracted. Okay, and then over here is another opposite ends of dipole attracted. Okay, so this is for covalent and this is for ionic. All right, let's talk about if we can write an equation to show the ionic compounds dissolving. Well, when NaCl goes into water, you get Na plus ions and Cl minus ions. Yes, you have to put the charge. Did I say you have to put the charge? You have to. When they're ions, they have charge. Okay, so here's some more examples. Ionic compound, metal and nonmetal. So we'll break them up. We got calcium ions, we got chloride ions. And then we check the periodic table for their charge, and we know they're dissolved in water. Now, I'm putting a 2 here. Why? Because every time this breaks apart, you get 2 of those, because when we put them together, we had 2 chlorides. So when they dissolve, we get 2 chlorides. Okay? So ionic compounds break into their positive and negative ions. It's magnesium nitrate. What are the ions? The ions are magnesium and nitrate. Okay, find the ions first. Second, go back and look for charges. Periodic table +2, memorized formula -1. This just means that 2 of them break apart. So then they become aqueous, dissolved in water. Woo! Yay! Okay, so conducting electricity, it tells you if you have an ionic compound or a molecular compound. Because which ones conduct the ionic? Why? Well, look at those ions. When it dissolves in water, there's these charged particles. But covalent, whoa, where we going? Covalent. Right here, covalent, when it dissolves, look, no ions, no charge, okay? So, wow, that was way back there, Harbin. Yeah, no, I went way back there. So, electricity just means moving charged particles. So, ionic compounds have ions that can move when they dissolve. Molecular compounds do not. Don't have any ions, no ions. So, ionic compounds are called electrolytes, conductors of electricity. Molecular compounds are called non-electronites. Vocab. Write it down. Get to know it. All right. Just to show you again, this light bulb is not on. No ions, non-conductor. This light bulb is on. Look, there's charged particles. It's going to conduct electricity, cause light bulb. This has a lot of ions. So look, bright light, electrolyte, non-electrolyte. Okay. So, hey, what's the deal with soap? So if you look at this molecule, you see this. This is definitely non-polar, right? But up over here on the soap molecule, there's this ion sodium. Oh, you can't see it? Okay. Ion sodium, ion of oxygen. There's ionic end to soap and a non-polar end to soap. So soap helps dissolve dirt. Yeah. So here's your ionic end, and here's your non-polar end. So if you have water, water's going to be attracted to this end because water's polar. This is ionic, charges attract. Okay. Well, what's attracted to non-polar end? Dirt. Hey, dirt, you're non-polar. You're attracted to non-polar stuff. So what happens is that the hydrophilic loves water. That's the side of soap that loves water. And hydrophobic is the side of soap that hates water. Ooh, boo, water. Ooh, water. I'm afraid of it. Hydrophilic, yeah, I love it. And so what soap does is it brings polar things with non-polar things, dirt, grime, goo, and so then those things mix together and get pulled off your skin. Yay, like still dissolves like. It's just that the soap molecules have both parts to it, and so they can bring things together. Yay. Okay, so because mixtures are physical blends of substances, you can separate them using physical techniques. All right, so here are 4 ways to do separations of mixtures. Please read them and know them, but they don't always work for every mixture. You can distill stuff if your mixture has 2 different boiling points. You can filter stuff if your mixture has different sized particles in it. You can crystallize stuff if your mixture has, one thing can evaporate off and the other thing can be a solid. You can use chromatography if your mixture has things with different polarity. Okay, so this is a technique, and these are the properties that are used for that technique. Now, of these 4 things, one of these will definitely not work for a solution. Okay, I want you to think about which one and put it in your notes, okay? All right, finally. Oh, hey, let's get some music going. A solution is a homogeneous mixture of many different states. Okay? Solid, liquid, gas. Alright? Solute particle is a small part. You get dissolved. Solvent is a big part. Solution is all parts. Alright? Whoops. That's for next time. Alright? This is important. Another way to say this is like dissolves like. Alright? Now, other thing I want you to do is use soap. Woo! Alright, we're done for today. Talk to you soon. Make sure you can do these. Alright? And go back and look. Hopefully you think you learned at least something about all these. Peace out.